Hello everyone, my name is Yun'an and I will present our paper on protecting data privacy in trigger action system. This is a joint work between University of Wisconsin-Madison and the Chalmers University of Technology. Today, Internet users are using more and more online services to manage their digital resources or cyber-physical IoT devices. However, these services are built with different APIs that don't understand or talk to each other. Therefore, we now have a special kind of services which we call the Trigger Action Platform, or shortened as TAP. TAPs connect functionalities from different services and perform automatic tasks. They provide a layer of abstraction that enables services to develop APIs independently without worrying about compatibility. Popular commercial tabs, such as IoT and Zapier, are connected to lots of online services to gather the required information to execute the rules. In this slide, we show two simple rules that automatically activate some smart home devices when certain event happens. These rules can also get a bit more complicated. The third example describes a rule that sends a warning message when there is a suspicious transaction happening, and it requires a number of condition checks as well as extracting a phone number from a string. However, as always, such convenience comes with a risk. TAP, by nature, is a cloud service, and the breaches of cloud services are commonplace. What would happen if these platforms were compromised? In this case, the attacker will have access to all kinds of private user data, such as chat logs, emails, and social networks. Even worse, they can control your smart home gadget, like a smart oven. We use IoT, which is arguably the most popular tab, as an example to showcase the security concerns. First, in IoT term of use, it explicitly states that they collect personal data from third parties and may share them with other third parties. And indeed, IoT does operate on lots of sensitive information. Currently, it has integrated with more than 600 services and has more than 20 million users, making it a very attractive target for attackers. In addition, previous studies have shown that the access token acquired by IoT from other services are overprivileged. So, if these tokens are leaked, the attackers can use them to access personal data even beyond what the rules require. Due to such security concerns, service like Gmail has already removed itself from IoT in the past. So, the problem we want to solve is how to design a system where the trigger action automation rules can be executed securely and privately. Our solution, eTAP, or Encrypted Trigger Action Platform, is a redesign of TAP that protects data privacy and integrity even if it is compromised. It supports common computations and especially optimized for string operations, which is very prevalent in automation rules. Also, our protocol is efficient with low overhead. First, let's abstract such example rule into a generalized model, where one trigger service sends the data to the platform to trigger the rule. The platform then computes a predicate function on both the trigger and some constant values provided by the user. If the predicate evaluates to true, TAP will continue to generate the action data and forward it to the action service. Our work is under the worst-case assumption that the attacker has fully compromised the TAP. That is, in our threat model, Tap is a malicious party that can do whatever it wants within its capacity. We don't want the attacker to learn the plaintext of the trigger or action data. The attacker can't modify or delay the action data without being detected. In addition, we want to ensure that the privacy guarantees of current tabs still hold, which means the trigger and action services are honest but curious parties, where the action service can't learn the trigger data or vice versa, and the action service can only learn the action data when the predicate evaluates to true. Finally, we need to establish a root of trust somewhere. In line with prior work, we assume that the user trusts its own client app, which is used to configure the rules. We imagine this client app to be maintained separately from the cloud component of the tab, and therefore we can decentralize the trust into each user. Only the client app should have access to the user constant. Some prior work have already provided some of these securities under similar threat model. Our work not only has this additional benefit, but also allows commutation in these rules. As usual, security consideration isn't the whole story when designing a system. Therefore, we need to have some practical consideration. For example, we need to ensure that there is little changes to the trigger and action services. Otherwise, there may not be incentive to participate. And we need to assume that the client, which is usually a phone or a computer, may not be always online. Our design is based on a cryptographic protocol called GoBot Circuit to provide secure function evaluation. GoBot Circuit is originally designed for two-party computation. In a traditional protocol, one party acts as the circuit generator, which is responsible for converting functions to circuit and encoding input data, while the other party acts as the circuit evaluator, which is responsible for evaluating the circuit and decoding output data. We utilize the unique structure in our system to fit such protocol. That is, the client and the trigger service together play the role of the generator, while the tab and action service together play the role of evaluator. One advantage of using GoBot Circuit in this setting is that it allows us to pre-compute the circuit before the input data is available, and the actual evaluation is very computationally efficient compared to other secure function evaluation protocols. ETAP extends upon this model to tailor GoBot Circuit to satisfy all the security goals we mentioned earlier, and we found that this asymmetry in trust assumptions actually leads to more optimization. Now, I will briefly go through each phase in a rule's lifecycle and overview what our system does at a high level. First, when the user first sets up a rule, it needs to go through an OAuth negotiation with both the trigger and action services to acquire the corresponding permissions. This is a standard step performed by every trigger action platform today. We extend the OAuth protocol to allow the client to exchange a secret key with both services. These keys will later be used as a basis of our protocol. Once the rule is set up, the client needs to periodically garble the function and stream them to the tab. First, we generate the encoding information with the trigger secret key and use it to seed the GoBot circuit generation procedure. This information is also used to encode the user-provided constant into GoBot constant. Finally, the client applies a symmetric encryption scheme to protect the decoding information with action key. The client needs to periodically stream the output of this step to tab. This is the trade-off we need to make for using GoBot Circuit, since a fresh circuit is needed for every execution. However, as I will show in our evaluation, the cost of generating and sending a circuit is very small. The last phase is the rule execution. The trigger service first computes the encoding information in the same way as the client, and then uses the encoding information to encode the trigger data. The tab, upon receiving the garbled trigger data, initiates the GoBot Circuit evaluation procedure to compute the garbled action data. The action service can decrypt the decode blob with its secret key to obtain the original decoding information, which in turn can be used to decode action data. Tailoring GoBot Circuit in these specific trigger action settings comes with many benefits. For example, we don't need to use oblivious transfer since all input data is provided by parties in the generator. In addition, since only part of the evaluator is malicious, we showed that by extending a semi-honest protocol with authenticity, it is enough to defend against a malicious tab without resorting to a heavyweight fully malicious protocol. There are many other interesting details about our system that I don't have time to talk about. For example, we are able to achieve GoBot Circuit authenticity with communication overhead proportional only to the security parameter, due to the separation between the evaluation party and the decoding party. Please refer to our full paper for more details. Okay, so until now, there is one important catch I have not talked about yet. In crypto protocol, every function is represented as a circuit. In theory, this is achievable. However, in practice, not every function can be converted to a circuit efficiently. So, in order to understand how many real-world rules we can support, we did a crawling of top if and Zapier rules to find the commonly used functions. Out of these functions, only a few are well studied and easy to implement. The majority of the functions are string operations which we need to craft our own solution. We noticed that many of these functions can be implemented through simple regular expression. So, the challenge is how can we evaluate regular expression efficiently in GoBot circuits. Now I will highlight the intuition behind our approach for string optimization. To evaluate a regular expression, we need to first convert it into a DFA, and then compute the DFA state transition circuit over and over again on the input string. We noticed that if we use one hot encoding to represent each state, then every OR gate in the circuit can be replaced by an XOR gate. In GoBot Circuit, a well-known optimization is that every XOR gate can be computed for free without any communication overhead. There are two remaining functions that our approach cannot efficiently support. However, as we can notice, both of them are purely formatting functions. In summary, ETAP can support over 93% of all Zapier rules and 100% of top IFT rules. For evaluation, we select 8 representative rules that covers all the common functions mentioned before, and found that our system on average has 55% increase in end-to-end execution latency and 59% decrease in maximum throughput. We also estimate the overhead of the client with the statistic in previous study. We found that the client only needs to spend 10 seconds per day to generate circuits that is enough for 1 day of use. And the total size of this circuit is just over 60 megabytes, which is equivalent to uploading 25 images or a 1-minute video. In conclusion, trigger action platforms provide desirable functionalities but pose great security threat if compromised. We propose eTAP, which is a clean slate design that protects data privacy and integrity against a malicious tap. We utilize the asymmetry in trust assumptions to optimize GoBot Circuit and efficiently support common string operations to ensure only a modest performance reduction. So thank you for listening to the talk, and I'm happy to answer any questions.